second speaker for today is Anne-Sophie Kaloghiros from Brunel, and she's going to speak about K-moduli of qubits.
Okay, so thank you very much for the invitation to speak and for such a lovely conference. So the goal of my talk this morning is going to be to describe the component of the K-moduli space M324 KPS associated to members of the definition family of Fano threefolds K-moduli04. Am I writing big enough? Yeah, okay, great. So let me repeat some of the things that Yu-Chen mentioned at the start of his talk in order to contextualize a little bit. So for X, the Fano manifold, or X delta a log Fano pair, I guess one of the most significant results in geometry in the past, I guess, 15 years is the proof of the Yao-Tian-Donaldson conjecture due to Chen-Donaldson's son, and then its extensions to a more singular framework by many people, including Chen Yang and collaborators. Which says that X admits, or X delta admits a weak Keller-Einstein metric precisely when X or X delta is K polystable. So as Yu-Chen mentioned already, a very significant consequence of all this, or a very significant consequence of the study of K polystability, is that K polystability turns out to be the right notion to kind of attack moduli of Fano varieties. And so, so we now know that there is a projective good moduli space MNV KPS whose points parameterize K polystable Q Fano varieties of dimension n and volume V, of dimension n and anticanonical degree. So a fairly classical question, or a fairly, was this question asked by Calabi over 50 years ago, which wanted to characterize the existence of Keller-Einstein metrics, because these are canonical metrics, but we can, so the Calabi problem asked which Fano manifolds admit a Keller-Einstein metric, which I guess after Chendon's and Son is the same as asking are K polystable, or can we understand K polystability? So we know a lot about Fano manifolds. We know in particular that in any dimension there's a finite number of deformation families of Fano manifolds. In dimension 2, there's 10 families. In dimension 3, there's 105 deformation families. Of Fano threefolds. And for each of these, we could ask several versions of this Calabi problem. The first one would be, is there or is the general member of a deformation family of the deformation family K polystable, and in Yu-Chen's talk that was essentially step 0 of building the step 0 of construction of K-moduli in Yu-Chen's talk. Well, more precisely, you can ask, is there a member of the deformation family, as Yu-Chen asked? Is there a member that is K polystable? And then by openness, it follows that the general member has to be K polystable. So this is equivalent to saying, is the component where we're talking about the associated component of the K-moduli space non-empty? So I'm going to follow the same notation that Yu-Chen used. Then the second question is a finer question. Which members exactly of the deformation family are K polystable? And then essentially the maximal version of the Calabi problem is describe the associated component of the K-moduli space. So I'm only going to be talking about threefolds, so let me just say 3V KPS. And here really, this includes, so describing this associated component includes describing all possible K polystable degenerations of smooth members of the family. So before I focus on the family I wanted to discuss, let me just say a few words. So here we have quite a few methods by now, or we have some methods to check K polystability. Of specific Fano threefolds or specific Fanos. So in particular, we have all the methods around Ivan techniques. We have the method that Yuchen mentioned in his talk, which is in the cases where you have some understanding of the automorphism group, looking at equivariance, so Zhuang's equivariant K stability. K stability. And then we have older techniques, or techniques that are now older, around alpha invariance, etc. I guess here, what I'm not saying is that a lot of the techniques I'm mentioning have to do with the valuative criteria of Fujita and Liu. So more on that later. But one thing for which I feel we have fewer methods is how to identify suitable K polystable limits or degenerations. And here we've already heard two talks on these topics during this conference. So here I'll refer to Hamid's talk yesterday. Also to elements in Yuchen's talk this morning. But then another general method is just being acquainted with the Fano base theory, so the zoology of Fanos. Okay, so in this talk, what I'd like to do is to tell you a little bit about this family. So perhaps start by saying a few words about geometry of the deformation family Mori-Mukai for one. Then you'll see that there is a natural GIT there. I want to discuss the GIT moduli, the associated GIT moduli. Another family of degenerations and then to conclude, I would like to give an explicit description of this moduli space K. Okay, so let me start with this geometry of this family. So the family Mori-Mukai for one is a family of Fano threefolds with Picard rank 4 and anticanonical degree 24. So they do fall in the range of Fano threefolds that Yuchen mentioned this morning. So these, we know a few things about these. One thing we know is the moduli dimension. So they have expected moduli dimension equal to 3. And Mori-Mukai also gives us a description of these as So X, a smooth member of this family, is a divisor of multi-degree 1111 inside P1 cross P1 cross P1 cross P1. Okay, so already from this description, this means that, for example, if I want to label the coordinates on this P1, 1, 2, 3, 4, so here I'm going to have x1, y1, x2, y2, x3, y3, x4, y4, then this tells me that x has an equation which is of the form x1 times some function f plus y1 times some function g equals 0, where f and g are equation of type are in H naught of P1 cross P1 cross P1, 1, 1, 1. So in particular, here, I think I'm going to regret doing that in about 2 minutes. Never mind. Okay, so here this means that f equals 0 and g equals 0 are both Del Pezzo surfaces of degree 6. Here I have quite a lot of geometry already from this picture, maybe. So I could imagine here projecting down to P1, to the P1 with coordinates x1, y1. Here I've got a fibration in Del Pezzo 6 surfaces. I've got a pencil of Del Pezzo 6 surfaces. I could also look at the projection to the 3 P1s with coordinates 2, 3, 4. Here, this gives me, it is easy to see that this is a blow-up in a curve f equal g equals 0. This curve here is the intersection of two Del Pezzo surfaces of degree 6. It's actually an elliptic curve. It's an embedded elliptic curve. So let me call that C. So this, any of these 4 projections to 3 of the 4 P1s is going to be the inverse of the blow-up of an elliptic curve. If I project down to P1 cross P1 here, if I project down more, I get a non-standard conic bundle which has discriminant curve the image of this f equals g equals 0, and that's a 2-2 curve on this P1 cross P1. So again, an elliptic curve. Okay, so this is all kind of to say that we have a very symmetric Fano threefold with lots of maps, lots of structure there. And perhaps I should say that the Calabi problem version 1 and 2 were solved in this case in work of Belousov and Loginov, who showed that that all smooth members of deformation family for 1 are K polystable. Okay, so
are they K polystable or K stable?
Turns out K stable. As an after. Well, precisely. Yeah.
I guess it follows from the GIT picture, or?
No, it follows from the fact that they are K polystable and they have finite automorphisms. For the so basically these Fano threefolds arise in another way, let me say a few words about this right now. So another description as an afterthought, you get it from the GAT as well. I'll explain why in a second. So another construction of MM41 is, let me give myself any curve C. It is not intended, but it doesn't matter that C and C are the same. And I want to consider the moduli space of stable rank 2 vector bundles. So stable rank 2 vector bundles with determinant, trivial determinant, and equipped with endpoints that are distinct in C. At each of these points, I want to give myself a, along with a line, LPI, in the fiber over each of the PI. So here, so this is a space of stable rank 2. So these are parabolic vector bundles. The stability condition is essentially, if you're looking without any markings, you have the usual slope stability for vector bundles. And you can use this parameter mu to kind of tune a little bit your stability condition to account for those lines. Turns out that when mu, the parameter mu is very small, the stability condition does not change. And I'm interested in the case small mu. So when the points are distinct, this is a smooth manifold of dimension 3 times PA of C minus 1 plus N. And so these have been studied quite a bit, these parabolic vector bundles. You can construct some modifications of those parabolic vector bundles centered at the parabolic points, the PIs. It turns out that in the case when, so in the case MS C3 for C, an elliptic curve those Hecker modifications give you a way to embed, to show that this is the blow-up of P1 cross P1 cross P1 along an elliptic curve. So this identifies your moduli of parabolic vector bundles with, so it is a member of family MM41, Mori-Mukai for 1. And so, as I said, you have these constructions well known to people who do vector bundles of Hecker modifications, which actually give you, in this case, some automorphisms of your threefold. And in particular, they give you that the automorphism group of such a smooth variety contains a copy of mu2 to the form, or so, and automorphisms contain a copy of mu2 to the form, or z over 2z to the form. Okay, so these will tend, so these members of this family will have finite automorphisms, but they have a lot of these, and as Eugen said, if you have a good understanding of the automorphisms, it gives you a lot of information to study K polystability. So let me mention the kind of happy discovery here. Is that these Fano threefolds also arise in quantum computing, as it turns out. They are, so Fanos in family MM41 also represent the entanglement of systems of 4 qubits. So qubits are mathematical models of the quantum analog of an ordinary computer bit, of a computer bit. So as far as I understand, they are just linear functions on P1. And so these systems of 4 qubits are correspond to these 1, 1, 1, 1 on P1 times P1 times P1. So perhaps, yes, but I didn't detail the stability conditions, but I guess that's fine. So let me move on to the description of the GIT moduli space. So here, just perhaps to refocus the discussion, I'm looking at these Fano threefolds, smooth numbers of which are divisors of multidegree 1, 1, 1, 1 in P1 to the power 4. So I'm looking at a space, a linear space of equations P1 times P1 times P1 times P1, 1, 1, 1. So this is a this has a 16-dimensional space of sections. It has an action. It has an action of gamma 0, which is the product of the SL2Cs corresponding to changes of coordinates on each of the P1s. It also has a linear action of gamma 0 semi-direct product sigma 4, where this is just the symmetric group exchanging the 4 coordinates. So, so the goal of this section will be to describe the semi-stable locus, or the GIT quotient here, there. But perhaps as a first step, I should say that one of the happy coincidences of this having some use in quantum computing is that these had been studied before quite extensively, and in particular, people had shown that if you give me one of these equations, F, which is a section of P1 to the 4, 0, 1, 1, 1, 1, then up to the action of gamma, F can be put in normal form. So I haven't written down all the normal forms, but this is essentially GABCD is going to be the one that I use in this talk. So I'm not sure how visible it is from the back, but the important message here is that this is an extremely, so we have a 16-dimensional vector space of sections. Here we have only 4 parameters, and these forms are extremely symmetric. So you can see that, that everything I've mentioned about symmetries of this Fano manifold is quite apparent in the normal form. So perhaps I should mention this as a proposition. So this is due to some people working in quantum computing. So I think the original paper was by De Streete, De Haan, De Moor, and Verschelde. There was a gap in that proof, which was corrected later by Sterndal and Djokovic. I apologize for my poor pronunciation of these names, but they prove that up to the action of my gamma 0 there, of gamma 0, the equation F can be put in one of 9 normal forms. So perhaps some facts going with this is that if the threefold defined by my form is non-singular, then the orbit of this equation F under this group has to intersect these families here. So then you can put up to gamma 0 action, you can put your equation in this form, which I call curly G for this family. So we only need to consider normal forms of this type, and this is really quite a simplification because, as I mentioned before, you can see that this is extremely symmetric as an equation. Let me get rid of the next ones. We also get immediately that the automorphism group of X has to contain a subgroup which is isomorphic to mu2 to the power 4. And we get also explicit generators. So let me just write those down. So this is the generator that exchanged the first 2 factors and the third and fourth. Then the second is the one exchanging the first and the fourth and the second and the third. And then the other 2 involutions correspond to, on each of the factors, P1, swapping the X and the Y coordinate. And here, this is the involution that sends xi, yi on each of the factors to xi minus yi. The only reason I'm writing this here is perhaps to illustrate in a little while how we use these to determine K-polystability, to determine invariance. So the last few facts is that if we have an isomorphism between the varieties defined by two of these equations. Then their orbits have to meet. And then also, so if you look at these equations, these are not all irreducible. There are some reducible ones, but they all belong to one orbit. So X is reducible precisely when F belongs to, F belongs to the orbit of gamma so D is 1 and the others are, so in my coefficients A, B, C, D, D is 1 and the others are 0. Okay. So from there, we get an explicit or a quite explicit description of the objects in this family. And I suppose I won't give too many details unless people want to know, but what we can find is that, so we find explicit invariant forms. So we find that if S is the symmetric algebra of the dual of V, then the invariance of the form C of HRST, where this has degree 2, this has degree 4, 6, 8, and 12, so that we get that the GIT quotient here is, so perhaps I should say this coincides with the action with the projectivization of this family G modeled out by the stabilizer of G gamma G. This happens to be the Veil group of the exceptional F4. And we find that this GIT quotient is a weighted projective space 1, 3, 4, 6. And we have the map from the projectivization of these Verstraete normal forms to the GIT quotient, which I'm going to call just P. The rest of this talk is a finite map of degree 576, I think. Okay. So what comes with this description is as well a fairly good description of the possible singular. Sorry. So the singular, the GIT polystable singular degenerations So let me perhaps just give this description. So if I write, let me write piecing here to be the locus of P in my weighted projective space such that that correspond to singular threefolds, then I get that this piecing has a stratification which corresponds, so these are disjoint sets. So I've got a locus corresponding to reducible members. I've got a locus corresponding to those that have a curve of singularities. Then I have a locus corresponding to threefolds with 6 ordinary double points, one with 4 ordinary double points, and one with 2 ordinary double points. So I should say that we can find, so if I call this map here P, pi, there, pi minus 1 of piecing, or so this is pi of the divisor in this projective space given by s cubed minus 27t squared of f equals 0. So my invariant ring, and I guess this is the locus s equal t equals 0. This is just one point, which corresponds to this 0, 0, 1 there. So this is, but in terms of these new coordinates, this is going to correspond to 1, 1, 0, 0 in the HRST coordinates. And then maybe I'm just going to leave it at mentioning that in there we have a toric Fano. So a toric example which was known, which corresponds to the one with reflexive ID 12645 in the graded rings database. Okay. So I suppose the theorem, or half theorem, that I'll hopefully say a few words about is that XP is K polystable for all P and P minus P reducible. So I should say right away that when P is reducible, corresponds to a reducible member, this stands no chance of being K polystable because it's not normal and therefore not KRT. But for all other GIT polystable limits, then these are indeed K polystable. Now, going back to Theo's question, I suppose that once you have these normal forms, the fact that all the GIT polystable quotients, and we'll talk about the other replacements later, it is probably enough to have this form to determine the automorphism groups in these cases. Okay, so I'd like to now present another family of degenerations, which is a different flavor, but also quite natural. And I think probably quite linked to some of what Yuchen was talking about earlier. The same sort of so my other family of degeneration is going to be so if you remember, I had my X that lived in P1 cross P1 cross P1 cross P1. And as Yuchen mentioned in his talk, there's a quite well-known degeneration of P1 cross P1 to P112. So we could look at the kind of families that we could get by degenerating the total space to P112 times P112. And so in this degeneration, so if you remember, this is my X is 1, 1, 1, 1. In these degenerations, the classical, I'll write it down in a second, will be sending a conic of type 1, 1 on P1 cross P1 to the section at infinity on P1, 1, 2. So let me write it down as this. Pretty awful notation, but so imagining that we're degenerating the total space, a possible limit of my X would be something of the form 2, 2 in a product of P112s. So what's the most general form of this type of threefolds? Well, the most general form of these threefolds. So if I write coordinates S1, T1, omega 1 on the first weighted projective plane, and S2, T2, omega 2 on the second. So the omegas are the weight 2 coordinates, and the SITIs are the weight 1 coordinates. I'll be looking at something of the form omega 1, omega 2 equals some function of S1, T1, S2, T2. Okay? And so F here is a section of P1 cross of O22 on P1 cross P1, where my first P1 has coordinates S1, T1, my second P1 has coordinates S2, T2. So here this P1 cross P1 is obtained by forgetting the weight 2 coordinates on both. Okay, so so let's look for a natural example here. Well, let's take the most symmetric example, omega 1, omega 2 equals S1, T1, S2, T2, and see what that gives us. And this turns out to be, again, toric. Well, this is made to be toric, so it is toric. So this is toric, and this is also in the graded ring database. Toric reflexive ID 610, I think. This is a canonical Fano threefold, and it is K polystable. So the general family that we'll be looking for is going to be, or we can look for a family where we allow, for example, F to be GIT polystable section of P1 cross P1, a GIT polystable 2-2 curve on P1 cross P1. So here is the family as I only have. So we look for a family of the form. So we look for threefolds that are defined as omega 1, omega 2 equals alpha times S1 T1, S2 T2 plus beta times S1 square, S2 square plus T1 square, T2 square plus gamma times S1 square, T2 square plus S2 square, T1 square. And so this is parameterized. So this is a family that I want to say is parameterized by 3 parameters, alpha, beta, gamma. So P2 alpha, beta, gamma, I'm going to say here. And so let me say a few words about the members of this family. So these are all singular along the curves that correspond to the product of the curve at infinity of one of the P1, 1, 2 times the vertex and the other way around. So this is C1 is S1 equals T1 equals omega 2 equals 0. And C2 equals S2 equals T2 equals omega 1 equals 0. But some members for some alpha, beta, gammas are more singular. We find, again, a stratification. So let me call E-sing those that have more singularities. So these are the P's in E such that X singular XP contains but is not equal to this C1 union C2. And here we have essentially, again, a stratification where this is an extra curve, a disjoint curve from C1 and C2, an extra 4 ordinary double points, which is the case of my toric reflexive ID 610 here. And then an extra 2 ordinary double points. So these can be understood entirely by looking at the singular GIT polystable 2-2 curves on P1 cross P1, which are either the double conic, so this is my curve of singularity, 2 smooth conics meeting in 2 points. This is my 2A1s, and the 4 lines give me the 4A1. Okay, so perhaps to conclude, I should say that it is possible. Okay, so. Okay, so I would have liked to have better managed my time, but I haven't. The point is that we can write down a degeneration that includes a family that will include both threefolds of the first type and of the second type. So it is possible when we start from my P3, which is the projectivization of this G here, and blow up the point that corresponds to the reducible the reducible members here, it is possible to write a family curly X that sits above there. And here, so if you remember, in order to go to the GIT moduli, MGIT, I was quotienting out by my veil group F4, looking at the stabilizer of the point that we've blown up here. We find that here there is a commutative diagram where here we're quotienting out by a, I should just not say that. So we find here that quotienting by the gamma action here gives us the blow up, a weighted blow up of this GIT quotient at the point that corresponds to my reducible Fano threefolds here. So here this MK that we obtain is a weighted blow up of the weighted projective threefold 1, 3, 1, 3, 4, 6 at this point with weights 1, 2, 3. So we can find a family which matches, and so perhaps granting what I'm about to say in a few minutes, the final theorem is that the K-moduli is that MK is a weighted blow up of MGIT at P parametrizing the reducible GIT polystable multidegree 1, 1, 1, 1 in P1 to the 4 with weights 1, 2, 3. So we have a quite explicit moduli space. Its pickled rank is 2, so we can understand somehow maps from this moduli space. It has this map to the GIT moduli space. It also has some other maps that can, to some extent, be understood. And perhaps what I wanted to say, what I have not hinted at, is how do you prove the K polystability of the threefolds parameterized there. So let me just say that in all cases, we use the equivariant results of the equivariant K polystability criteria due to Zwan. So if not K polystable, or before I say this, so I'm out of time, but if I can just take 30 seconds to say So in the case where F is in G, we can find, as I said, the automorphism group containing this mu2 to the power 4. Then so the valuative criterion tells me that X is K-polystable if the beta invariant of any prime divisor over X is greater or equal than 0. Zhuang's criterion tells me that if this fails for a G invariant prime divisor over X. So it's enough to look at things that have centers on G invariant, G equivariant loci on X. And because we have this quite explicit description of these tau 1, tau 2, tau 3, tau 4, we're able to study directly what these G invariant loci might be and apply Ivan Zhuang to well-chosen flags around these. So I'll stop here. Sorry for going over.
Can I ask you, you mentioned this alternative description in terms of moduli-space parabolic bundles. Can you translate your knowledge of moduli space in terms of the mark curve?
We're thinking about it. So one thing, the reason why I mentioned this approach was in the spirit of what Yu-Chen said earlier. You don't want K stability to be an island. So we want to connect to other K-moduli ideas. And so one result, for example, by Facerella and Justo is that if the moduli space of parabolic vector bundles on two elliptic curves with 3 marked points are isomorphic, then this gives you an isomorphism of the elliptic curves. So this suggests that at the level of moduli, you have this map from MK to the Jacobian to P1, classifying the Jacobians of your curve. So somehow knowing the threefold, so you have a sort of Torelli theorem that identifies the curve from the threefold. And so at the level of moduli, you should have a map from your moduli to P1, which classifies the elliptic curve. And actually, when you write down the weighted blow-up with weights 1, 2, 3 of your GIT space, you can see a birational contractions to this a birational contraction to P1. Now there's something else happening in the middle, which I don't understand.
I think the Torelli theorem is not just there for the elliptic curves; it's there for the marked elliptic curves. So you should get a map to MG. M13, and you should pick up some of the compactification of what M13.
Yes, but that should be somehow the fibers of. We have like P112 bundle over P1, and I expect that this is in the P112 bundle. But yeah, I'd like to hear your thoughts about it. Yes.
So what are the homogeneous coordinates of the blow center?
On there, so in terms of the invariance, it's 1, 1, 0, 0.
So what is happening in the stack? You also have a stacky blow up. You know what's happening with semi-stable stuff though?
I don't.
So that's one normally, that's one for instance that the stack is non-singular?
I don't think so.
It's a current block. It's a weighted current block, right?
Yeah.
Are you sure?
I mean, we know that deformations are unobstructed.
Well,
so it's
quite true.
Yeah.
But you don't have a description of at the stack level, and for instance, with this map, you were saying we map to M bar 1, 1, or some genus 1 plus something. And that it's usually easier to construct a morphism at the stack level because then you have a universal you just have to construct a universal family. You haven't tried that.
So Kento's written down this family that kind of that is over this projectivization. Is that right, Kento? But does that say more about the stack?
But for stack, we need the description of case semi-stable members, which we don't know.
You don't have to prove everything that is case semi-stable.
We need at least to describe characteristics.
Also, you have the stable and the polystable, but not.
Yeah. Okay, we have a lot of examples of case semi-stable.
No, it wasn't a criticism, it was just a clarification that this was part of the issue.
It should be possible, but using different technique. Basically, you can approach should be, I guess. Yes, you can. Your approach should be applicable to describe case semi-stable.
I do.
The degree is big, 24.
Oh, thank you.
Then what's the difficulty to categorize the semi-stable?
If we know that they all live in the spaces, then they're not difficult.
But why don't we just calculate the deformation space? If it's a certain dimension.
Yes, we didn't do it.
Why not?
It's not finished yet. Thank you for advice.
If not, we can turn it.